Hey there, welcome to another video. So in this video, we're going to talk about the graphs of secant and cosecant. And it's going to be pretty fast because we're going to relate them back to sine and cosine so that they're just reciprocals. We're going to use the fact that they're reciprocals and that graphs are based on sine and cosine for cosecant and secant respectively. So we're going to take a look at that and it should be pretty straightforward. So let's take a look first at cosecant. If cosecant is the reciprocal of sine, so cosecant x is the reciprocal of sine of x, we can base the graph of cosecant on the graph of sine. In fact, there's a lot of very interesting things that happen. And when we start graphing with transformations, what I typically do is I'll graph the sine version of that function and then just draw cosecant right on top of it. Or for secant, I'll graph cosine and then I'll graph secant right on top of that. So because they're so strongly related, because they're reciprocal functions, we can use sine and cosine as very nice tools to graph cosecant and secant. So let's take a look at sine. If sine of x is this nice curve that repeats every 2 pi, so we have 2 periods of sine right here, shown in a dotted line so we don't get confused on what we're actually doing. Here's what's going to happen with cosecant. Because cosecant is the reciprocal, let's take a look at some of the reciprocals of the values that are on the sine of x function. Firstly, let's look at all the local maxima and minima. Well, what we remember is that sine has peaks at +1 and sort of valleys at -1. Well, if we take a look at the point pi/2, 1, which is on the graph of sine, well, the reciprocal of 1 is still 1. Because cosecant is the reciprocal of sine, since sine of pi/2 is 1, cosecant of pi/2 is also 1. And so we have a point there. The same thing is going to happen at -3 pi/2. So sine of -3 pi/2, that's +1. So cosecant of -3 pi/2 is also +1. The reciprocal of +1 is +1. The reciprocal of -1 is also -1. And so we're going to have those points. So at -pi/2, sine of -pi/2 is -1. Cosecant of -pi/2 is also -1. The reciprocal of -1 is -1. And that happens here and here. Now, the interesting things happen at the zeros. So where sine of x equals 0, what's the reciprocal of 0? Well, this would be 0 over some sort of a constant. Usually it's 0 over 1. If I reciprocate that, that's 1 over 0. And so here's what this means. This is one of our key features we're going to write down in a minute, is that we're going to have vertical asymptotes everywhere we had an x-intercept for sine. So if we have an x-intercept at 0, hey, sine of 0 was 0 over 1. Cosecant of 0 is 1 over 0, and we're going to have a vertical asymptote here, and at pi, and at 2 pi, and at -pi, and at -2 pi. Every place where we have an x-intercept for sine, we're going to have something that's undefined, a vertical asymptote for cosecant. So if we're going to base this cosecant x off of sine of x, well, then we have sine of x, and we said, yep, reciprocate, and we still have 1, -1, -1, 1. Reciprocate our x-intercepts of 0 over 1, we get 1 over 0. That's undefined, that's vertical asymptotes. And there's only one other real value that we kind of need. That would be this. If you have sine of pi/6, sine of pi/6 is 1/2. Remember, cosecant is the reciprocal. So if sine of pi/6 is 1/2, cosecant of pi/6 is 2 over 1. Well, what that means is that where sine does this, cosecant does this. The reciprocal is the flipping of that fraction. So we're going to get everything that's above 1 and below -1. There's not going to be anything between -1 and 1 on the graph of cosecant x. So sine of pi/6 is 1/2. Therefore, cosecant of pi/6 is 2. And due to the nice symmetry that we get, we can kind of extrapolate from this. So I didn't put a lot of the pi/6 and 5 pi/6 and things like that, just because, well, we kind of know what sine looks like. And if we have that one point and use some symmetry here on all of our quarters of our, well, halves of our periods, then we can get a really nice graph. So this is really what we do for sine and cosine, changing into cosecant and secant. We graph sine, we change it into cosecant by just reciprocating points. We graph cosine, we reciprocate our points, and we get secant out of it. That's how I'm going to do all of our transformations too, is just through this process. So let's finish up our graph. They're not quite parabolas, but they almost look like it. It's a really weird graph, right? I mean, sine is this nice, smooth curve, has no discontinuities. The domain is all real numbers. You can plug in anything. You only get out values between -1 and 1. Because cosecant is the reciprocal, we actually can't get out anything between -1 and 1. -1 is the, let's call it, smallest negative value we get, and +1 is the smallest positive value that we get. In terms of absolute value, 1 is the smallest value that we get. So we get all the way down to -infinity and all the way up to +infinity. It's really looks like a disjointed graph. I hope it makes sense where it comes from. It looks kind of funny because we have to obey our vertical asymptotes. Our reciprocals told us that we climb. If these numbers on sine are between 0 and 1 for this particular portion of our x-axis, well then when I reciprocate that, I get values larger than 1. If I reciprocate something very close to 0, I'm going to get something very close to infinity. And that's what's happening. So this is the look. The purple is the look for cosecant x. It's based on sine of x. Now let's write a couple things about it. Firstly, the domain. Because our x-intercepts of sine cause vertical asymptotes for cosecant, we're going to have domain problems. A vertical asymptote every place we had an x-intercept for sine. Well, that was at 0 and pi and 2 pi and 0 plus k pi. I hope you remember that. That's what we had for x-intercepts. Well, now that's going to cause vertical asymptotes for us. And so our domain says we can't have 0 or any multiple of pi from 0. That's what that says. We can't have 0. That's a vertical asymptote. It used to be an x-intercept for sine. Now we reciprocate it, we get a vertical asymptote. 0 or +1 pi or +2 pi or -1 pi or -2 pi. All of those are vertical asymptotes because they came from x-intercepts. That should make sense. Now our range. We actually cannot get anything between -1 and 1. We get above 1 and we get below -1. And how we write that for our range is -infinity to -1. We actually do get -1. There is a point there. And then 1 to infinity. We actually do get 1 and everything above that. And so that's our range. Now the period. The period's the same as sine. So the period is 2 pi. You can see that it repeats. Here's 2 pi, another 2 pi, and it repeats every single 2 pi. So if we had to draw several cycles, we would just go 4 pi, and then 6 pi, and then 8 pi. And we draw the same exact thing. Very similar to sine. In fact, I always draw sine first before I draw cosecant. And finally, the key features of this graph. Just remember that we get vertical asymptotes every place that we had x-intercepts on sine. The reason why I'm saying it that way is because I'm going to encourage you to draw the sine function first for all of our transformations that we're going to do for cosecant. Draw the sine function first, like a dotted line like I've done. Draw your vertical asymptotes on x-intercepts and then draw cosecant. It's much easier than trying to memorize what that looks like. If you have it, great, but this is a tool to get you to memorize it. So that's the idea. And that's really it. Cosecant is the reciprocal of sine. Let's go on to secant x. So because secant x is the reciprocal of cosine x, we're going to base it on cosine. That's what I've done for you right here. I have this nice dotted line that shows 2 periods of cosine. Here's -2 pi to 0, 0 to 2 pi, that's 2 periods. We're going to do exactly the same thing that we did for cosecant. Now, I hope you remember this. I hope that you remember that cosine is like a shifted version of sine. It's a phase shift. Well, what that means is that secant should be a phase shift or a shifted version of cosecant. And so that bears out. And so we're going to do something very, very quick, very, very similar to what we've done. Firstly, remember that secant is the reciprocal of cosine. So if I have 1 and -1, -1, 1, 1, oh, the reciprocal of 1 is still 1, so I'm still going to have points there. The reciprocal of -1 is still -1. I'm going to have points there as well. Remember, cosine of pi over 2 was 0 over 1. That gave us 0. Well, that means secant is going to be the reciprocal. So the secant of pi over 2 is 1 over 0. That's now undefined. So we run into the same situation. We ran into here that x-intercepts on sine cause vertical asymptotes on cosecant. X-intercepts on cosine do the same thing for secant. So we're going to have a vertical asymptote at every x-intercept for cosine. Now, it should look really familiar because we just did it, but we're going to do something very similar with pi over 3 that we did with pi over 6. Cosine of pi over 3 is 1/2. It's right there. So that means secant of pi over 3 is the reciprocal of 1/2, or 2. And due to some symmetry, hey, it is an even function. And using that fact, we can get a very similar graph to cosecant. That's about how secant x looks. It's just the reciprocal of cosine. I hope it makes sense. I hope that you're seeing where these are coming from. This is how I go ahead and graph pretty much all my transformations with cosecant and secant. I just graph sine or cosine and then reciprocate it. So show these almost parabola-like looking things. From the fact that we're reciprocating, we know that it's above 1 or below -1. Here, the same thing. Our range is either below -1 or above +1. We get the same exact range here. Our domain it's shifted. It is shifted. Notice that. This is a shifted over version of this. It's a phase shift. That's all it is. But what our domain is going to be is every place where we had an x-intercept on cosine, we now got a vertical asymptote for secant. That happens at pi over 2 plus k pi. So plus pi over 2 plus pi would be here, pi over 2 minus pi, minus another pi. We're going to get a vertical asymptote at all those things. So let's write that out. Our domain says, yeah, because it's based on cosine and because x-intercepts happened at pi over 2 and every multiple of pi, we say that x cannot equal pi over 2 plus any multiple of pi. That's going to give us some problems. It's going to give us x-intercepts for cosine, and therefore vertical asymptotes for secant. Our range is the same thing that we got for cosecant x. And so is our period. Because this is based on cosine, a period of 2 pi is the same for both cosecant, sine, secant, and cosine. So they all have the same period there. Now it looks a little funny because the period here cuts our graph right in half. So that's a little bit awkward. A lot of times we're going to kind of think of this as one period, especially when we have, actually for inverses we think about it a little bit differently. We have to cut it so it's 1 to 1. But we can sort of alter where we think of that starting or stopping. So anyhow, our period is 2 pi, and the key idea here is that this is based on cosine. What that means, because it's a reciprocal function, is that where we had x-intercepts on cosine, we're now going to have vertical asymptotes. And that's really about it. So what I'm going to show you now is just 2 examples of how we can do some transformations with cosecant x and with secant x, and I'm going to base them on sine and cosine. All right, let's do an example about a transformation. We'll have one more after this one. Let's take a look at 4 secant 1/2 x. Here's the first thing that I do. Because I'm so very comfortable with cosine and sine, what I do is I graph I pretend that is whatever the reciprocal function is. I pretend that is cosine for just a second. I graph a dotted line version of cosine and then I reciprocate it. For me, that's a lot easier than actually trying to remember what secant looks like and where that period is in my head. That's quite hard to do, or at least it used to be. And so this is the way that I practice doing that. And so what I'm going to do right now, I'm going to pretend that that's 4 cosine 1/2 x. Now, it doesn't help if you can't remember that secant is the reciprocal of cosine and not sine. So that is a problem. I've seen a lot of students forget and do cosecant is the reciprocal of cosine because they both have co in it. It's not, it's opposite. So the reciprocal of secant is cosine, the reciprocal of cosine is secant. And so I'm going to draw 4 cosine 1/2 x. Because secant is the reciprocal, this is going to work just fine for us. We're going to graph a dotted line version between -4 and 4 in this particular case. We'll see that with the transformation. And so what I've done is really made this like several videos ago. I'm just going to do this as far as transformations are concerned. I'm going to do all the transformations on that particular function and then just reciprocate. It's going to be very easy. So let's take a look at it. If I'm just going to graph 4 cosine 1/2 x, I'm going to first look for a vertical shift. Now, we don't have any, but that's what we would do first. Hopefully you remember that we would shift up or down based on whatever's being added, subtracted. Then I'd find my period and put it on my graph. It's super convenient because the period for both secant and cosine are 2 pi. Remember that the period that we have to find for this particular function is 2 pi, because that's both cosine and secant, divided by whatever that is. So dividing by 1/2 is really multiplying by 2. This is going to give us 4 pi. I stop right there and I start putting this on my graph. You're also going to notice that I go at least a full period to the right, and I go at least a half a period to the left. And the reason is because, especially with secant, this is going to cut part of that graph. It's going to look a little funny, so I always do half a period to the left as well. Try that, hopefully it'll benefit you as well. So I'm going to do 4 pi. So 4 pi, half of that's 2 pi, then we have our first quarter pi and our third quarter 3 pi, and I've done negative pi and negative 2 pi. This is half a period to the left, and that's what I want. I want to show that so I get a complete graph out of this. I don't want to start cutting it. So try that on your own too. Make sure you do at least a full period to the right and half a period to the left over the y-axis. Now we're going to have to deal with our key points. So remember that our key points for cosine are, we have x-intercepts at the quarters. So first quarter and third quarter give x-intercepts. Remember that with cosine, we have the start of the period, comma 1. At the middle, we have -1. At the end, we have +1. So those give us our 3 key points for cosine. I really hope you remember that. I hope that you remember with cosine, because I really do need you to know that, because if we're going to base this on cosine, that we really need to understand that. That's why we did the video that first. So cosine says, yeah, if you have 1 period, then you're going to put that into four quarters. So the start and the end, the midpoint, and then the 2 quarters, first and third. So with cosine, you start with a period at 1. And then you go first quarter 0, second quarter, that's right in the middle, -1, third quarter 0, fourth quarter at +1. That's what we have. We have start at 0, 1. Then the first quarter, we have an x-intercept, great. At the second quarter, or right in the middle, we have -1, we're going to be down here. At the third quarter, we have an x-intercept, and at the fourth quarter, the very end of it, we're going to have +1 again. Now, because we have this factor, because that 4, yeah, we're going to affect our key points, but man, I hope that you're seeing what it's based on. All cosine says is, yeah, take your start, your middle, and your end. Those are your key points. Now multiply 1 and -1 by that 4. And what this has done is this is going to vertically stretch this graph of cosine. It's also going to, because we're going to reciprocate it, vertically stretch the graph of secant. This also is taking and horizontally stretching out our period into 4 pi. It's twice as long as normal. And so it's going to make it really wide. So a stretched out and stretched out graph. So we're gonna plot that right now. Again, with cosine, you really need to know that the x-intercepts happen at the quarters and the peaks and the valleys happen at the center and at the ends, and that's what our key points do. Because we're basing this on a key point idea, because we have that, just multiply whatever your output factor is, that factor times your outputs, and we have that. So let's do 0, 4. 2 pi comma negative 4, and 4 pi comma positive 4. We'll also get negative 2 pi comma negative 4 because of that idea. That would be the center of a period. We're going to get the same exact key point out of that. And now we graph it. Now I'm going to use a dotted line because I don't want to confuse this with the graph we're trying to get. I'm just going to do this. Now that we have that graph of cosine, it's really easy to do the graph of secant. All we need to understand is that because this is a reciprocal, vertical asymptotes are going to occur at our x-intercepts, just like that. Now, all we have to do is remember that secant is the reciprocal. So we still have these points on secant. Let's just graph above and below, as the case may be, and we get a very nice graph of 4 secant 1/2 x. It has the same period. It's going to have the vertical asymptotes where x-intercepts were on cosine of the same type of function. We just base it on that cosine. This is what I found is the easiest. I hope it works for you. I hope you're seeing the interplay, and it's a really good tool. It's really good for remembering that secant is based on cosine. It'll help you to remember that, and it'll help you to graph with a lot of the transformations, especially like phase shifts and things like that. So hope the technique works for you. I'm going to come back with one more. Okay, last one. We're going to take a look at negative 2 cosecant 2 pi over 3 x minus 2. That's a lot going on. The first thing I'm going to do is think about the reciprocal function. The reciprocal function is sine. And so I'm going to think of this as sine. Now, with that shift, that shift in my head of, okay, I'm dealing with sine now, I'm going to go through the entire process with sine and just draw cosecant above and below it. Not a big deal. So this has a vertical shift of down 2. I'm going to write that. I'm going to show that. Then I'm going to find the period. The period for sine and cosecant is both 2 pi. So we're going to take 2 pi and divide by 2 pi over 3. So 2 pi divided by 2 pi over 3, the 2 pi's are going to cancel. You get 1 divided by 1/3. That's 3. So I'm going to show that. And just for fun, I did 2 periods here. So I did 2 cycles of this. So remember, our period is 3. This would be 1 cycle, 2 cycles, 3 cycles. So I have 3 periods of this sine function right now. Then what I do is I find my key points. Remember that with sine, our x-intercepts happen at the beginning, middle, and end of each period. So we have x-intercept here and here and here. That's our beginning, middle, and end of that first period. Remember, the period is 3, not 6. And then we're going to have key points at our quarters. So +1 and -1 at the quarters. So we'd have, originally, what we would do here is we would have the first quarter positive one, third quarter negative one. And so we've shown that, we figured out our period first that we would know our quarters. We have that down, and now we're going to modify that. That -2 is going to multiply the outputs, so that's going to stretch this and reflect it. So there are actually 4 transformations. There's a shift down 2, there's a very slight horizontal, actually considerable horizontal compression from 2 pi under 3, and now we have a vertical stretch and a reflection. So we're going to take that, multiply the outputs of our key points. Let's go ahead and plot that. Now, please remember with this key point technique, it works from where you shifted to. So our x-intercepts, yeah, they're really not x-intercepts. They're on this shifted version. That's what we do. It's just a nice graphic organizer. I know it's not really there, but it's a very good place to graph from. You're going to see it especially when we graph that cosecant function. And now we're going to go ahead and say, hey, the first quarter was originally first quarter 1. It's been stretched and reflected. Now it's first quarter -2. But from here, so first quarter -2, third quarter +2. And we're going to graph that. And we can mimic that in the next period and the previous period and get a very similar type of graph in both those intervals. That is the graph of -2 sine 2 pi over 3 x minus 2, shifted down, compressed horizontally, stretched vertically, and reflected. I am just really hoping that you understand the interplay between the key points, what that does, and how it is done from where you shifted to. This acts like your x-axis for this technique. I've been teaching it a long time. Now that we've done that, all we have to do is understand that where our x-intercepts are, we're now going to have vertical asymptotes. And I hope you see why I'm teaching you this technique with the key points interacting with that sort of new x-axis is because the vertical asymptotes interact with that too. So where our x-intercepts are here on this is where you're going to get those vertical asymptotes. That's why this technique works so well. So all we have to do now is understand that, well, cosecant is the reciprocal of sine, and so we graph from these local maxima and minima. And we get a fairly decent look for relatively little work. If we really needed to, we could erase the sine function here and get a nice cosecant function. That is, the solid graph is this -2 cosecant 2 pi over 3x minus 2. I hope you like the technique. It's what I've come up with as the best way to graph it without really having to put in a lot of time because we're so good at sine and cosine. Just think about sine and cosine with your key points. Remember that you have to shift and treat that like your x-axis, and then everything falls into place. Use your first quarter and your third quarter for sine as far as your key points, and your ends and center for cosine, and then reciprocate to get cosecant and secant for sine and cosine respectively. One more thing. Please remember that because the range of cosecant and secant is -infinity to -1, and 1 to infinity, you will not get x-intercepts on those graphs. There aren't any x-intercepts on cosecant or secant until you start shifting them around like we've done here. So I hope that makes sense to you as well. They don't exist unless you start shifting it. We have some here, but that's just because we shifted down so far. All right, hope that makes sense. Have a great day. I'll see you for another video.